So I have a question about the homework. So are you gonna be moving the homework for that was assigned for this week to next week? You know what I mean?
Circuits homework?
Yeah.
I thought it was already moved. Am I mistaken on that?
Oh, I don't know. I haven't checked.
So last Monday, I think I pushed like 3 assignments back.
Okay.
So
Okay.
yeah, I think it's
Sorry.
not due until next Monday already. So that one's already taken care of, if we get there. Yeah. Yeah, go ahead, Isaiah.
I have a question about the number 4 on the electric potential homework. It has the 3-point charges arranged in a square. And it asks for the electric potential at the fourth corner. I got that, and then it asks for the electric potential at like a coordinate. I don't really know.
Yeah. So it like asks, yeah.
Like 1, 5, 0.
Yeah. So it's something like, yeah, it has some coordinate system, and it's located at L and some distance L on the vertical axis. And then, yeah, you've got, a point charge located here. You've got a second point charge located at LL, and a third point charge located here. And then for part B, it basically asks you to consider some field point way out here. Right, so for part A, you're looking at the field point right here at the origin. And so you have to get, these distances and calculate out the potentials. Yeah, so for part B, you just have some location out here in space. I don't know what your specific numbers are.
1, 5, 0.
Okay, so it's like an L, a 5L, and a 0. So for example, if you want to get the distance from, say, this charge in the y-axis, oh, that's a terrible line, but to that field point location, right? What would that distance be? How many units do you go in the x direction? 1. So it'd be something, no, not to scale, of course, sorry about that. But yeah, so you're going basically 1L in the x direction, and how many steps in the y direction do you need to take?
5.
Well, 5, except you're starting at the one that's, already up in position L. So yeah, so here you would go 4L up. Wow, that's okay, okay, order's restored. Yeah. So to get the distance to that field point from this upper left-hand charge, you could do something like this, and L squared plus 16, so you'd have something like the square root of 17 times L for that one distance. But then you got to rinse, wash, and repeat for the other 2 charges. So in some sense, it's the exact same problem as question A. It's just that for A, the distances, you can almost see them right away, whereas for question B, you have to do a little bit more trig and algebra to get the distances.
Yeah, for A, it was like K Q1 over R1 plus K Q2 over R2.
Yeah. Yeah. And I apologize, I guess that since this field points at L, each of you get something different here, right? But for that field point, I guess I should have drawn it over here somewhere, but yeah, that goes on. Other questions? Yeah.
So on one of them, it talks about a wire and a cylinder.
Is that the electrostatic precipitator? Yeah, I set it to 0. I set that problem to 0.
Okay.
Yeah. No, I think it was Ben who was talking to me about it, and I was like, oh yeah, I gotta put in this little extra piece of information. And then maybe it was it Cassie that was talking about it? I can't remember. Cassie came in later, and I was like, oh yeah, you got this new piece of information. I got halfway through, and I said, oh, and I don't even remember what the problem was, but I go, oh, and so I set it to 0.
Okay.
Yeah. Mhm.
Is it, that was 7 and 9, is it?
I think now it's 7, 8, and 9. I think the electrostatic precipitator was the one in the middle, maybe. Yeah, so it's 7, 8, and 9 now. Yeah. And they've been struck from the future records of the class, but yeah, yeah. I gotta think, I mean, I would like to I think I need to replace it with something like an electrophoresis problem, which is the exact same idea. It's just, instead of it at Clifty Falls power plant and being cylinders, it's Cartesian coordinates. So it's just X and Y's instead. So I gotta think about how to do that and write something up. Unless you guys wanna write something up. That sounds like a great test question. Write up a sample problem for an electrophoresis. Oh, by the way, you gotta write it up so a 185 student will understand it. So you can't just Wikipedia it because, you know, let's face it, you Wikipedia and it talks about Reynolds numbers and Adas and there's a bunch of Greek letters and I don't understand what they mean. Right? You say Reynolds number and I'm like, okay, I'm out. Peace. Yeah. Something with fluid dynamics. I don't know exactly. So, yeah. Other questions? Yeah, some measure of how well fluid flows over the surface of an object. Something like that. Sorry, I did remove the problem in terms of weighting it, but it is kind of interesting to at least read how it works. So, yeah, okay, so you can't answer any of the physics questions, but there's a whole paragraph there that's essentially you've got the physics basis for how it works. A charged particle enters the bottom, it sees an electric field to the outer wall, and so it gets, it gets pushed to the outer wall where it's get collected. So the charged particles being pieces of ash, pollutants. So you remove that before the air gets all the way out of the smokestack. So that's how you scrub some of that dirty smoke before it actually goes in the atmosphere. I think fire detectors might actually work the same way. I'll have to write it all. Yeah, okay, okay. So there's something else, so we'll keep going on with this thing about combining capacitors. We already had an idea about the distances. So if you have capacitors that are in series, two capacitors, and they can be the same capacitor value, they can be different capacitor values. But if you had something like this and you wanted to replace it with a single capacitor, the question is, what would the value of this new capacitor need to be in order to behave the exact same way as the two capacitors in series? And by behave the exact same way, I mean store the exact same amount of charge, have the exact same potential drop. So in terms of the function of the circuit, these two would be completely identical. And the idea was that, this is called a series arrangement. The final, answer is that the capacitance would be given by this equation. I'll give you more general here. So if I take the sum of the individual capacitors, if I take the sum of the inverses, there we go. I wanted to say the inverse of the sum. So if I take the sum of the inverses of the individual capacitors, that will give me the inverse of the equivalent capacitance. Now, there was a question that was raised, why is this important, or where would this actually come up? And I gotta admit, I struggled with that one for a while. And then I was really trying to think of some place where that maybe it would be more familiar to you, and I was just failing miserably. But one of the things I do know where it comes up. So here's the issue, and this is more of a practicality side of things. From a physicist mindset, and you'll see it in your homework problems, I just pick numbers. Like I pick random numbers, right? I say, oh, you have a capacitor of 10 microfarads, or you have a capacitor of 2 microfarads, or I just pick a random number. In practicality, though, from a manufacturing point of view, they do not provide an infinite number of capacitor values. from a manufacturing point of view, if you go to Radio Shack, remember the days of Radio Shack? You could go into Radio Shack, you pull up in this drawer and just have a selection of capacitors in front of you. Okay? But from a manufacturing point of view, manufacturers cannot produce every single number known to person for capacitor values. So you open up the drawer at Radio Shack and you will see specific set values for the capacitors. You'll see like 1 microfarad or 3 microfarads. And you say, well, but I need a 2 microfarad. And they would say, tough luck, you need to combine the ones that we actually have to get the one you actually want. Right? Because manufacturers do not produce a 2 microfarad capacitor. They do 1, they do 3. And if you want a 2, you're going to have to figure out a way to finagle it to actually get that to work. So that's one place where it comes in that, you design a circuit that needs a certain capacitance, and then you try to go on and get it and find out that doesn't exist. So you have to combine them in some way to get the thing that you actually want. Now, I don't know, again, I was struggling with biology and just trying to, chemistry or biology and trying to think of some creative way of, some situation where this would come into play. And then I realized that the body also doesn't produce an infinite number of cells. Now, I don't know if this will equate or not, but I know, for example, like eels store charge, right? The eels will, if you think about it, an electric eel, how does it actually, shock things? It stores the separation of charge. You can model that as a parallel plate capacitor. And then when it gets close to something, it discharges the capacitor, electrifies the surrounding water to shock its fish, and I don't know what happens after that. Some sort of biology. I don't know, maybe it swallows it whole or something, digestive tract. Okay. But the standpoint of that would also be the same thing. Well, how does an eel get such a large capacitance? Well, it takes individual capacitors, something, I assume it's something with one of their cells, and arranges them to get a larger equivalent capacitance than what the individual cells would provide. Again, I'm sure the devils are in the details, but I know that in general, right, how do you get such a large shock out of such a small cell? Well, it's that you've arranged these cells to get a larger equivalent capacitance than what each individual cell would provide. And now I'll set you off and running. I don't know, does it do that in the book that you borrowed for the electric eel? Didn't you borrow a physics book from me? Yeah, does it have it in there? I don't know either, you'll have to go and look later. Yeah. So that's at least one place where I said, okay, at least I could theoretically see where this is useful. Now, in a matter, again, a practical matter of actually getting out the details, that's a different issue. But I know that the body can't produce an infinite number of types of cells. Just like a manufacturer can't produce all ranges of capacitance. So you're stuck with the ones that are available, and you got to build stuff from there. Same, if you ever get into guitar players, anybody like to get into guitars or building amplifiers? Okay, I see some shaking. Yeah. Same thing. If you're designing an amplifier circuit, you'll have to, you'll find that you want capacitance that aren't available, and so you'll have to mix and match. And if you really get into it, I know this is probably not your shtick, but if you really get into it, you start having to ask yourself, which capacitors are more expensive? Maybe the capacitor actually exists, but it's so expensive that you could do a bunch of cheap capacitors and come out economically cheaper than if you just bought the regular capacitor that does the thing you want. So there's also a cost to benefit thing going on there. I don't know, in biology, how would that work? Well, I could build that cell, but it'll cost me more energy than if I build 6 of those cells and just run them in a certain way. I don't know if that works or not, but. Yes, I'll be the stereotypical physicist, and I'll say, okay, I want to incorporate biology. I'll just drop cells every once in a while, right? I'll just name drop it. Yeah.
So how does that equation work?
How does this one work?
Yeah.
If you want to replace a series of capacitors of known value with a single capacitor, this equation will tell you the value of the single capacitor that's needed. So again, if this is like 5 microfarads and this one's 10 microfarads, and you want to replace that combination with a single one, what we would have to do is do something like 1/10 plus 1/5. So what is this? Common denominator. So we get 3/10. And so the equivalent capacitance, the equivalent capacitance would need to be 10/3 microfarads. And then again, from the standpoint of the circuit, this would function exactly the same. That's if they're in series. The question is, what happens if I put them not in series, but the other term is called parallel? In other words, what happens, well, I should say, any other questions on that? Sorry, I'm just jumping into new stuff. I gotta look up that electric eel. I should just.
Is this going to be on this test or the next test?
It seems like this one should be on the next test. Yeah, that seems fair.
So would this test be all the way up to electric potential?
Yeah, that seems okay. We'll just do this one all the way up to and including electric potential and electric potential energy. Yeah. But we'll save the, yeah, this one's always a weird one. I would prefer to probably talk about resistors first, because resistors tend to be something that I think people are a little more familiar with. But because you're sitting there talking about electric field and electric potentials, the capacitor is how you store the electric field in a circuit. So I can kind of see why they put it in here, but it feel really discombobulated if you went, to the resistors and then came back to the electric field later. So, so yeah, there's just some organization just doesn't have a really good way of doing that. So that's with capacitors in series. How about if we put them in parallel? And I think I left you with this one. Conceptually, let's say you place 2 capacitors in parallel. Conceptually, what does this actually, well, okay, sorry. First off, parallel, you could say it's not series. Well, that's not very informative, right? I mean, so series, we said, hey, if the charge goes through the path, it has to to get to the second capacitor, it has to go through the first. Okay? Just like I gave the example, the World Series, before you get to game 7, you have to go through games 1 through 6. That is the only way to get to game 7. So parallel is, fielder's choice, if we're going to keep going with the baseball terminology. Okay. You have choices. You can go one way or go the other way. To get to capacitor 2, you don't necessarily have to go through capacitor 1. You have options. Okay. And so the question becomes, how does this change? So if I have 2 capacitors in parallel, what happens to the overall capacitance? So I took one capacitor, and now I stick a second one next to it. What happens to the overall capacitance? Does it go up? Does it stay the same? Does it go down? It increases. Okay. Conceptually, what you could think of is, rather than thinking about 2 parallel plate capacitors, think about the fact that you basically, wires are free. So that's almost as if you increase the area of the capacitors. And if you remember from our equation for the parallel plate capacitor, we said that the capacitance of a parallel plate capacitor is directly proportional to the area. It's inversely proportional to the distance between the plates, and it's directly proportional to the area. If I increase the area, I can increase the overall capacitance. And you could probably take a stab at what you think the relationship is. I'm just curious. What's the relationship here? What do you think if I had 2 capacitors in parallel? Draw that in. If I had 2 capacitors in parallel, and I wanted to replace it with a single capacitor, what do you think the value of that new capacitor, that equivalent capacitor would be? How would we find it? Just add the two together. It's almost like you took the areas and just added them together. You put two capacitors next to each other, you increase the area. You say, well, conceptually, by how much did I increase the area? Well, you just took the sums of the two areas. So, yeah, if I call this C1 and C2, and I'm sure I have this on another slide, so I'll write it here, but I'm sure I've got it somewhere else too. The equivalent capacitance will simply be the sum of the individual capacitors. Warning. I mean, I do it too, but I beg of you, try to at least conceptually think about what's going on before you write down the equation. Because if you just memorize straight off, parallel situation, I add them, series situation, I do the inverses. If you just try to straight out memorize it, I guarantee you'll get it wrong at some point. You'll screw them up. You'll flip them. So try, if you can, no, I do it too. Sometimes I memorize it and I'm not thinking. If you can, try to conceptually remember what's going on underneath the surface. Right, putting them in parallels, like increasing the area, that means that my capacitance should add. Putting them in series increases is conceptually like increasing the plate distance, and so my capacitance should go down. And I warn you of this because it depends. Okay, you'll have to correct me again, and I apologize. Did you guys deal with springs in 161? Did you deal with springs in parallel? Did you deal with them in series? Okay, I'm seeing shaking heads. The only reason I ask is because you actually get some relationships like this with springs in parallel and springs in series. In fact, do I have it on here? Maybe doubles the area, yeah, blah, 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 blah. I can't remember. So I'll use this blank slide, this semi-blank slide. The same thing, I mentioned it, the same thing happens with springs in parallel. Say, and series, say you have two springs of spring constant K1 and K2, and you want to replace it with a single spring of spring constant KEQ. Sorry, I gotta remember this for a second. Yeah, okay, got it. Sorry. See, I know it's one way or the other, and I gotta make sure I get it right. Right. So the question is, what happens here? You end up with KEQ. It's the exact same relationship, although that summation sign looks like I had too much coffee this morning. So it actually ends up at the exact same relationship. And if they're in parallel, so you put two springs in parallel, and you want to replace it with a single spring, the exact same relationship. KEQ will equal the summation of KI. So if you get comfortable with this idea about capacitors, you can backtrack that knowledge back into springs if you need to, for whatever reason. And we'll forward track that knowledge because guess what? We will see this again with a different circuit element called resistors. Except the relationship's exactly the opposite. In other words, if you do it in series, they add, and if you do it in parallel, it's 1/overs. Which is why I give you the warning, don't try to memorize it, think of the underlying idea and then go by that. Because if you try to memorize it, then you'll screw up resistors in series as versus capacitors in series at some point. Or you'll screw up the equation for capacitors in parallel with resistors in parallel at some point. So just be careful. And I'm sure I have a chart here at the bottom of the slide. Yeah, parallel plate. There we go. Of course, I spent all that time writing it in, and then I've got it written up here. Sorry, I called it effective. Sorry. When I was writing it down, I put EQ as an equivalent, but then in my notes here, I used the word effective. Same idea. Questions? And you can run into situations where it's a combination of them. Right, so do I have a blank slide? Oh no, I was talking about energy here. So you could run into situations where maybe you start off with a capacitor. I'll draw it sideways here. And then maybe you get a choice. Right, something like this. So you have two capacitors that are in parallel with each other, but then they're in series with a third capacitor. And so you could, first, I mean, like, yeah, C1, C2, and you can step through it. Well, first of all, pretend that you combine the two in parallel to get an equivalent capacitance, and then that equivalent capacitance is in series with the third capacitor. So you can take these and kind of build it up. And heck, for kicks, you know, you can put another one right here, there. Okay, we'll call that C4. Boom! No. Dynamite, I guess it's not dynamite, but still. This doesn't have the same ring to it, yeah.
I remember in lab, they showed us a picture of a circuit and there's two little lines like that at some point. Does that mean a capacitor? But one of the lines is a lot bigger than the other.
Yeah. Yes, we have to be careful. Yeah, so you're right. When we get into, well, we're getting there. But yes, since the question's been asked, capacitor, the symbol for a capacitor, you always draw parallel plates. Even if it's not a parallel plate capacitor, two parallel lines is indicative of a capacitor in a circuit. Okay. But you are right that there's unfortunately another symbol which looks a lot like a parallel plate capacitor. And you know what, sorry, some textbooks, and me as well, will use two parallel lines of the same length. Some textbooks will use a curved line. So you'll see it like this. One straight line and like a curved line, which doesn't look very curved. Okay, let's try that one more time here. We can do it. 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 We can help her, Cinderella. Okay, something like that. There's not supposed to be a dot there. Either one of them. Come on now. I worked so hard on that. I sang. Okay, anyway, you get the idea. The other circuit element that looks very similar to this, and that's why I think some textbooks use this notation. The other circuit element are two parallel lines, one dramatically shorter than the other. Okay. That is to represent a battery. All right. So when you see two parallel lines, one dramatically shorter than the other, that's a battery. So that's probably what it, or if you prefer, sometimes people will interchange a battery for just a constant potential source. So we'll say a battery, but it could be, you know, some power supply unit. And it's providing a constant potential, so I don't know. Yep. And I think I have a summary slide. After I get done with this energy bit, then I think I have a summary slide that gives you the rest of the circuit element symbols while I'm at it. So you have a light bulb, you have a resistor, you have an inductor, you have a capacitor, and I think that's all we need to worry about. But other questions? So the last thing that probably should, I mean, I promise that, hey, capacitors are a way of storing energy. And specifically, they store energy in the electric field. You pack charges onto the top plate, that forces charges off the bottom plate. Because you now have some separate charges, you have created an electric field inside this tiny circuit element. There is energy associated with that storage, and you can remove that energy if need be. And in fact, like, yeah, these are like how AEDs work, right? It charges up the capacitors, and you want to discharge them very quickly. You know, through a AFib patient, hopefully. Don't do that if you're not in AFib. So the question is, how much energy is actually stored? So I'm going to go back. Let's start off with our relationship between the change in potential energy and a change in potential. So I started off with that. Change in potential energy is simply the change in potential that a charge Q moves through. So if I move Q through a potential of V, this will tell me how much potential energy has been gained or lost. Of course, that depends if it's rolling downhill or if it's rolling uphill. But now we have an expression for the change in potential energy of a capacitor. If I have a capacitor, what's the change in potential energy of a capacitor given by? Maybe I'll put an equivalent sign here. We define, I'm just taking our definition of capacitance and rearranging that. So pretend, the question is, let's say I want to move a charge through a difference in potential of the capacitor. And I want to know the change in energy of that charge. We're going to do something even more specific. Let's say, because I'm interested about how much energy is stored inside the capacitor, let's say that I take some charge from the top plate with my tweezers, and I very carefully move it to the bottom plate. And I do it again, and I do it again, and I keep doing it. Okay? So in a very controlled manner, I take charge from the top plate and very carefully place it on the bottom plate. As I do that, what happens to the electric field inside the parallel plate capacitor? Does it increase or decrease? As I move charge from the top plate to the bottom plate. Quick, how do I create the electric field in the first place for the capacitor? Difference in electric potential. How do I generate the difference in electric potential? I separate the positive and negative charges to create the potential difference, or to create the electric field between the plates. I had to get the charges separated. So as I recombine the charges, in other words, I have less separated charges, what should happen to the electric field in the capacitor plates, between the plates, as I have less charges that are separated? It decreases, which means the potential difference between the plates decreases. As I move charges from the top plate to the bottom plate, I decrease the electric field strength, or I also decrease the electric potential. You can think of it as the potential difference between the plates gets smaller. The lines, the equipotential, there's not as many equipotential lines between the plates as I move the charge. Okay, so the question is, can we figure out how much energy is released if I take all of the charge from the top plate and deposit it on the bottom plate? So what I have here, let's say that delta Q represents that tiny amount of charge that I pluck off of the top plate and drop onto the bottom plate. It's a tiny amount of charge that I've moved. And because I'm moving it across the potential difference of the capacitor, I've just plugged in that capacitor divided, the charge of the capacitor divided by the capacitance. Next question. Let's say I start off with some total charge, Q total. After I do that first tweezer move, after I pull some charge off the top plate and put it on the bottom plate, how much charge is now on the capacitor? The top plate. So after I pluck some delta Q off the top plate and dump it on the bottom plate, what's the charge of the capacitor now? It's a little less. If I start off with a total amount, after the first move, I have a little less. How about after the second move? A little less. A little less. After the third move, a little less. After the fourth move, et cetera, et cetera, et cetera. Okay. So as I move more and more charge from the top plate to the bottom plate, the charge on the capacitor decreases. Okay. I'm going to take that and sub it in right there. I think. So I'm saying the initial charge on the capacitor minus, I put an I here, which is probably a bad choice, but I mean I to mean the number of moves. And then I can't spell moves, and I moves. In other words, how many times have I plucked a charge from the top thing to the bottom? Now notice, on the right-hand side, now I'll move over to the right-hand side here, I've got a graph for you. I have plotted on the horizontal axis the amount of charge that has been moved. And on the vertical axis, I am plotting the charge on the capacitor. And you notice there should be a one-to-one relationship, right? As I move some charge, the capacitor should decrease by the same amount. So I've drawn in a 45-degree line with a negative slope. As I move some, as the number of charge that I move goes up, the total charge on the capacitor remaining should go down by the exact same amount. Okay? Follow me so far? So after the first move, let's say I is equal to 1. Or maybe, I'm sorry, let's say for the first move. Yeah, so I is equal to 1. I am moving a small delta Q of charge. And if you will, the potential of the capacitor is given by Q over C. Okay, maybe Q minus delta Q. Fine, we'll be over C. In other words, that's the height of this bar. So to find the total potential energy, I just need to find the area of that bar. right? Delta Q being the width, excuse me, I should say, the height being Q minus delta Q. And so if I take Q, delta Q, the amount I've moved, times the amount of charge still on the capacitor, that would be the area of that rectangle. And I simply divide by the capacitance, that tells me how much energy I've released. Question for you. And I do that, I keep doing that, right? That's for the first one, now I do it again for a second one. I move my second delta Q. The charge on my capacitor has decreased a little bit. I multiply those two values and I divide by C. And I do it again, and I do it again, and 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 again. What's the area what's the area? Maybe I should ask that. Right, I have to do this for each little small rectangle. What's the total area beneath the curve? No, I'm not asking you to do calculus. I'm asking you to do geometry.
The area of the triangle.
The area of the triangle. What's the area of the triangle? 1/2 base times height. Don't freak out. I'm not asking you to do calculus. I'm asking you to do geometry. Right? You hear area beneath the curve, you're like, oh, calculus. I don't know. This is stupid Professor Robinson. He's not supposed to do calculus. I'm not. I'm asking you to do geometry. Yeah. You notice the area beneath this, I mean, it's a triangle. So the area is given by 1/2 base times height. Oh, what's the height of this triangle? Q, right? The starting charge of the capacitor. What's the width, or the height is Q. What's the width or the base of the triangle? The charge that's moved. How much charge, what's the total amount of charge that I can move? Take some from the top capacitor plate, move it to the bottom. I do it again. I do it again. I do it again. I do it again. At some point, I'm going to run out. In other words, the amount of charge that moved is also the initial charge that's on the capacitor. Right? Eventually, right here, that's also Q cap. Right? I cannot move any more charge than what was initially on the capacitor plate. Which means the height of the triangle is the charge, the initial charge on the capacitor, but the base of the triangle is also the initial charge on the capacitor. And so I get an area of 1/2 the initial charge of the capacitor squared. There we go. So I say, okay, well, I guess the charge of the capacitor times the charge I'm moving, and I thought that I had this in here, so I'll just write it in. 1/C, let me rewrite it. I'll say Q squared over 2C. That's the total amount of energy. When you take a capacitor and you charge it up, you've got it all charged up, and then you turn around and you want to discharge it, the total amount of energy that you can discharge from that capacitor is the charge of the capacitor Q squared divided by 2C. Now that's not sometimes helpful, because that requires you to know the charge on the capacitor, which might not be too intuitive. It's okay if I erase this up here. Q total. All right, I realize that. Okay. So that might not be intuitive. Let's use this. You notice that I have a Q squared over C. The potential drop across the capacitor is given by Q over C. So I could write the energy stored in a capacitor can be the charge squared of the capacitor over 2C, or equivalently, using this relationship, I could write that as, let me think here, 1/2 the capacitor times the potential difference across the plate squared. And that second expression might be a little bit more helpful. Right? I charge up the capacitor plate. The potential drop across the capacitor plate is whatever I'm using to charge it. If I use a 1.5 volt battery to charge up my capacitor, when my capacitor is fully charged, the drop is 1.5 volts. I disconnect it, and now I've got that one, I can find out how much energy do I have stored here. Or say I take the same capacitor and I hook it up to a car battery, 12 volts. When I unhook the capacitor, I now know the potential drop across the plates is 12 volts, and then I can, discharge it or use that energy somehow. So it depends on what you say, which equation do I use? It depends on what information you have. Do you know how much charge is on the plate? And then say use the first one. Do you know what you used to charge the capacitor in the first place, the potential drop? Then use the second. And of course, this is where eels get really, right? Like the eels, like charge up the plates and they have all this stored energy. A little small puffer fish comes by and they zap it. It's like a little lightning strike in water. I think, right? I'm not smoking something. Right? That's how the electric eel spends their prey, right? They just parallel plate capacitor, fish swims by, they discharge all of the energy into the surrounding water, zap the fish. And then they take it to the sushi chef, and then they cut it nicely and serve it up. Anybody have puffer fish? I'm not a fan of sushi, so I figure if I can't handle raw salmon, then toxic puffer fish is out of the question. No? Maybe? Yeah. You've heard of this, right? Puffer, I think it's puffer fish. Yeah. No? If the chef prepares it wrong, if they accidentally nick a gland, then the food is poisonous. Yeah. And it's apparently really nasty stuff. Yeah, okay. You see, you know more about it than I do. Although you guys will have to tell me this fad with the tree frog poison. I just don't understand it. So there's something about cleansing that's going on in California. New York Times had an article about it maybe a month ago. But apparently they take toxic tree frog venom and they put it on your skin and it induces vomiting for an hour. And then people say it's a very cleansing experience, and there's people that do it multiple times and everything. I'm sorry, but vomiting for an hour, no. And apparently it's almost instantaneous. They scratch their skin, they put it on there, and within 15 seconds, they're horribly vomiting for hours. Okay, so it's not just me that was reading this thinking, man, this is weird. Okay.
It says vomiting can cause throat cancer.
I'm sorry?
Vomiting too much can cause throat cancer.
Oh, yeah, there's the soft, yeah. I don't know, and part of me wants to see if it's true, just to try it once. Does it really work that fast? But then I'm thinking, vomiting for an hour? No, forget it. I hate throwing up once. I can't imagine just going for, anyway, okay. Questions? So again, essentially where this equation comes from is literally take tweezers, pull the charge from the top plate to the bottom plate. How much energy do you get off by moving, getting those charges from one plate to the other? Now, of course, I kind of give you a conceptualization, you pluck it off and drop it on the other one. In reality, you connect the top plate to the bottom plate with a wire. Right? So that's the same thing. You're taking your top charges and moving them to the bottom. How much energy gets released? Move them from the top to the bottom. And generally you hook that wire into something else, right? You don't just want to release it and run it back through. You want to do something with that energy as the electrons go from the top plate back to the bottom. So you put in a little light bulb or something. Oh yeah, that's the emergency. In the spirit of snow that hasn't arrived yet, You know, like those are little those little battery flashlights. Or not the battery ones, like the hand crank ones that you have like in your car sometimes. Because we all know if you keep the battery flashlights in the car, you know the one time that you actually need it, you pull it out and the batteries will be dead. All right, so you get those little hand crank ones so that it doesn't use batteries. Well, how does it store the energy? You turn the little crank, there's some magic going on in there that we have yet to talk about, but essentially it drives electricity onto a parallel plate capacitor. And then when you turn on the switch, it's discharging the parallel plate capacitor through the light bulb to keep the light on. Now, yes, you probably already suspect, does the current stay constant when you do this? No. So it'll start out bright and it'll slowly get dimmer and dimmer and dimmer as the current begins to decrease. And then you sit there and you crank it a little more and it gets bright again, and then after a while it'll get dim again, and then you gotta crank it again. Oh, I do have it. Oh, okay. Oh, yeah. Okay. There are no questions. That's all I have to say about that. Life is like a box of chocolates. If you don't get that reference, I feel sorry for your childhood. Please tell me you get this reference. Life is like a box of chocolates. You never know what you're going to get. Forrest Gump?
Again with a Forrest Gump.
No? You've never seen Forrest Gump?
No.
Oh my goodness. Your homework for next weekend is to go and watch Forrest Gump.
No.
Okay? Right? Everybody else has seen Forrest Gump, right? Okay, we can laugh at D for not seeing Forrest Gump. Have you no soul? You don't like Tom Hanks?
I watched telenovelas growing up, but then.
Huh?
It's not the best movie.
Yeah, but it's Tom Hanks. He's like America's sweetheart, right? Tom Hanks catches COVID. It was like, holy cow, this stuff got real.
I don't even know who that is.
Oh, okay. Yeah, sorry. I'm not very starstruck, but I got to admit that if I saw Tom Hanks, I'm shaking that man's hand. I'm sorry, sir. I'm sorry to disturb you. I just appreciate all your work. Big, Splash, Apollo 13. Anyway. Road to Perdition. Okay, I think there was some questionable behavior there.
Last way.
Ooh, demons. But by and large. Okay. Get rid of this. So the last piece I'll throw in for the capacitors is this dielectric stuff. And you, as long as you feel comfortable with capacitors, maybe not combining them yet, but you're starting to get a little more comfortable with conceptually what's going on here, then you have everything that you need in order to understand what happens with the dielectric. We're going to take two pieces that we've already talked about. Number one, the capacitors. And the second piece that we're going to now put in is what happens to a material when you expose it to an electric field. Okay. This is Greg rubs balloon on his head and sticks it to the wall. Okay. So let's imagine for a second we have a charged up capacitor plate. So I've drawn in the electric field here, and I've taken the liberty of drawing in the equipotential lines. They're evenly spaced throughout the entire capacitor. And the question becomes, what happens if I throw a material in between those two capacitor plates? Okay. Now, usually, again, you want a material that is an insulator. If you put a conductor between those two plates, the charges on the top are going to zip down to the bottom and you'll be done. Okay. So this only has a practical application when you put an insulating material in between the two. Over on the right-hand side here, I have a little blob that is supposed to represent an atom of that insulating material. And when you take a material and you expose it to an electric field, what are the electrons and/or nucleus going to do? If I take this happy atom, and I expose it to an electric field pointing down, what are the electrons going to want to do? Move up. What is the nucleus, the positively charged part of the atom, going to want to do? Move down. Right? This is what we called an induced polarization. I called it induced polarization. You might know it as an induced dipole moment. But the idea is this, right? Because of the electric field due to the capacitor, the negative part, the negative charge of the atom wants to shift upwards. The positive nucleus of the atom wants to shift downwards. And you induce a polarization. If I think about that separate charges, because of the electric field due to the capacitor, I have now generated an induced electric field due to the polarization of the atoms. Right? Electric fields point from positive to negative. So because I have separated the electrons and the protons, I have an induced electric field inside my material pointing up. Is that okay so far? You following me still? Due to the electric field of the capacitor, the dielectric polarizes. There's an induced dipole moment. And the induced dipole moment of the material points in the opposite direction of the capacitor, the electric field due to the capacitor. What happens to the overall electric field in the capacitor? Right, the net field. As I insert the dielectric, what happens to the magnitude of the net electric field between the capacitor plates? Quick, electric fields obey the principle of superposition. If I want the net electric field, what do I have to do? Add up the individual fields. Well, now I have a field due to the capacitor, and I have a field due to the polarization of the material in the capacitor. And so if I want the net electric field, I need to add those two fields together. So the overall, the net electric field is smaller than the field of the capacitor, right? Opposite direction. So I get a net field that is still pointing down, but is less and smaller in magnitude than the original field of the capacitor. What can you tell me about the spacing of the equipotential lines? If the electric field has decreased, what happens to the spacing of the equipotential lines? Go ahead, talk to your neighbor. Get an idea. If the electric field between the capacitor plates has decreased, what can you tell me about the spacing of the equipotential lines? Oh, do I have any more tea? Oh yeah, I do. Oops. There we go. You have an idea? Oh, what was that? chair backing or something. Okay. Oh, is that you? Oh. You got an idea? More time, less time? Yeah, how do we relate the electric field to the electric potential? Or given the electric potential, how do we get the electric field?
Changing potential.
The change in potential gives you the electric field. Or a different way to say it, the slope of the potential gives us the electric field. So if the electric field is smaller, that means the slope is less steep, which means what happens to my equipotential lines? If I want a less steep slope, do they need to be closer together or do they need to be further apart if the slope is less steep? Farther apart. Right, topographical maps. Lines that are close together, steep slope. Lines that are far apart, shallow slope. So by inserting the dielectric, I induce an electric field in the material that decreases the overall electric field, and therefore the spacing between my equipotential lines increases. Oh, come on. Oh, I had an animation, I swear. Oh, I don't. Okay. Oh, I thought I had it. Sadness. Epic fail. So the spacing of the lines increases. Next question. Spacing of the line increases. Or a different way to say it, the potential drop from the top plate to the bottom plate is smaller. Right, delta V is smaller. We'll write it here. Delta V goes down. What happens to the overall capacitance? If the difference in potential from the top plate to the bottom plate goes down, what happens to the overall capacitance? It increases. Yeah. The capacitance is defined as the charge over the difference in potential. If delta V goes down, that means the capacitance must increase. Dielectrics, inserting a material between the plates of a capacitor, are a way of increasing the capacitance without changing the size. You can store more charge for the same geometric shape by simply inserting a dielectric. From a practicality standpoint, you remember I said parallel plate capacitors from manufacturing, they usually start them out parallel plate and then they roll them up like a pumpkin roll or a Swiss roll, a little Debbie Swiss roll. Okay. Now, when you do that, you want to make sure the plates don't touch, right? Otherwise, the capacitor, doesn't work. So what they do before they do that rolling procedure, they put a plate, they insert a dielectric, they stick the second plate, then they roll it up. Okay. So from a practicality standpoint, it also helps you make sure that you don't accidentally touch the capacitor plates. I mean, like they don't accidentally touch during the manufacturing process. From a practical standpoint, I also said there's a limit to how much charge you can dump on a capacitor plate. This will hopefully give you a sense of that. If you make the electric field of the capacitor so strong that you rip the electrons out of the dielectric, okay, then you have now damaged your capacitor. It will no longer work. Okay. If you put too much charge on the capacitor plates, the electric field will get so large that the electrons will be ripped off of the dielectric. You'll ionize the dielectric. And at that point, you essentially have a spark travel from one plate to the other, and that destroys your capacitor. I'll have to find an image. I don't think I have any in my office anymore, but capacitors, they introduce a weak spot on the top. They put a little crosshatch, a little X on the top, so that if that ever occurs, and the capacitor, basically it'll blow a little, you blow a capacitor. What that means is that current has traveled through the dielectric and destroyed it. They put a little crosshatch on the top and it will bow outwards when you blow a capacitor. And the reason they do that is so that when you open up the machinery, you can see which capacitor failed, and so you can pull it out and drop a new one in. They purposely introduce a weakness so that you see it. Oh yeah, rooms with centrifuges are the same way. You guys deal with centrifuges, right? Dealt with those? Usually you don't put a centrifuge into a really, like a bulletproof room. Okay. What you do is when you put a centrifuge into a room, you make sure that one of the walls is weaker than the rest of them. So that if the centrifuge ever blows up, you know exactly which way the explosion's going. Okay. You do this if you ever have any hazardous materials or something, you always make sure that you always make sure it's in a room where one of the walls, you know where it's going to blow. Incidentally, you make sure that that wall blows to the outside of the building, not towards the center of the building, right? Blow it away from people, not towards people. So, anyway, okay, what do we got? Oh yeah, 1 second, 1 minute. Okay, as promised, okay, yada, 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 it makes the field weaker, the lines. The last piece I'll give you, and then we'll start with circuit elements on Friday. Today's Monday. We'll start on circuit elements on Wednesday. If you want to take into account the dielectric, usually nothing changes except that you now have what's called the dielectric constant. So this K is called the dielectric constant. If you're dealing with air or a vacuum, it's 1. If you're dealing with any other material, it's some value greater than 1. 2, 10, 50, it just depends on the material. And I put down here, some people, rather than having a dielectric constant times the permittivity of free space, some books will lump it all together and call it the permittivity of the material. If you ever see the word susceptibility, you're dealing with the same stuff. If you ever see susceptibility is related to the polarizability or the electronegativity. If those words mean anything to you, those are all tied together. It's when I expose it to an electric field, by how much does it separate? Okay, we'll pick up with resistors on Wednesday. We'll start off with batteries, and we'll start moving into circuit stuff. So, hey, thanks for your attention. I'll see you Wednesday.